where we will give a short introduction to approximation. Specifically, we will approximate the very hard problems of vertex cover and knapsack. So we assume for now that everyone already knows about the vertex cover problem and the basics of P and NP. In fact, if you look around this same basic site where you have found this video, you should be able to find a video called Vertex Cover is Hard, which goes through all the details of vertex cover and explains exactly why vertex cover is NP hard using this figure here, which you might then recognize. So we leave that aside for now. Basically what we take away from that video now is that vertex cover is very hard. It is not likely to be in P unless we have the big P equals NP collapse of the complexity hierarchy. It is still a practical problem, so ideally we would like still to solve it. Luckily, there exists a polynomial approximation of vertex cover. That is an algorithm which finds a cover that is at most double the size of the optimal cover in polynomial time. That is, whenever you have a graph G where there exists a cover of, say, size k, then we have a polynomial algorithm that can find a cover that is of size 2k, it is no longer the optimal cover, but at the very least you have found some cover, and it is not entirely outsized or entirely different in size from the optimal one. So this is what we would call a polynomial 2 approximation for a problem. That is, a polynomial C approximation for a problem P is a polynomial algorithm which finds a solution that is at most C times worse than the optimal for every instance P. So this algorithm is in fact very easy. So if you just imagine that we have a graph that looks something like this. What we do to find a 2 approximation, that is, we will now in polynomial time find a cover that is most twice the size of the optimal one, is that we pick any edge in this, like so. Then we go on and pick, again, any edge, as long as this doesn't touch a vertex of an edge already picked. So we cannot pick this edge, and we cannot pick this edge. We can, for example, pick this edge. And again, we go ahead and pick another edge such that we do not touch a vertex already picked. So we cannot pick this, we cannot pick this, we cannot pick this, but we can pick this. So at a certain point, we will have picked as many edges as is possible. That is, we can now no longer pick any further edges. And at this point, what we do is that we include every vertex that is in such a picked edge in the cover. So we say that we take the cover which contains this vertex, this vertex, this vertex, this vertex, this vertex, and this vertex. So now this actually looks fairly terrible because what we have done is we have found a cover by covering all the vertices. But in fact, this will necessarily only be at most twice as many vertices as is necessary to find a cover. And the argument for this is very easy, in fact, and that is if you look at an edge like this, the fact that this edge exists means that one of these vertices must be included in a minimal cover. If neither of these vertices is included, then this edge is not covered. So this means that in picking both of these, we have picked at most one vertex too many. And in picking both of these, we have picked at most one vertex too many for this, and in this case, one vertex too many. So in fact, there cannot exist a cover smaller than a 3 cover for this graph. And in fact, if we just get a little bit luckier, because we have now just picked the edges arbitrarily, but we could of course have ended up picking edges slightly better. So let's say we ended up picking that edge, and we ended up picking that edge, then we have chosen all of these vertices, and again we have a cover now only of size 4, which is still a little bit worse than the optimal should be. Yes, because we can pick as optimal that one, and that one. However, the approximation doesn't have to end up as bad as always being entirely double, because we might get a little bit lucky in how we choose the edges, but we will always be within a factor 2 of the optimal solution. So this is then a 2 approximation of the vertex cover problem. We just keep picking edges until we have what is called a maximal matching, that is edges that do not touch. and then just mark all of the vertices in picked edges. So this may not seem fantastically impressive, but still it runs very quickly. It's not that we just have to, in linear time, keep picking edges until we have sufficiently many, and it gets us something that is within some bound of being correct. Not all problems do really have a useful concept of less than optimal. Certainly the satisfiability problem, that is when you have a propositional logic formula and you want to know whether exists a variable assignment that makes the entire formula true, cannot really be said to have an almost correct answer, because if you have to cheat and not assign one variable or say that this variable is both true and false, it doesn't really hold a very deep relation to the idea of solving the satisfiability problem. So for the problems which have approximations should in some sense be optimization problems, that is, we are trying to find a minimal something or a maximal something. And in that case, we may be able to find a polynomial C approximation. Not all problems that are minimization or maximization problems have polynomial C approximations either for any C, which is of course unfortunate. Still, C approximations are a useful tool, and in many cases they are really all we need to get a solution that is sufficiently good. But the real crown jewel in the theory of approximations is the idea of the polynomial time approximation scheme. So what is this? Polynomial time approximation scheme for a problem P is an algorithm which as input takes an instance of P together with a constant epsilon, which is greater than 0. And this algorithm then computes a 1 plus epsilon approximations of that instance and does it in polynomial time when epsilon is considered constant. That is, the algorithm is precisely a scheme in that we can choose how close we want to get. And as long as we consider that choice of how close we want to get a constant, then we will get an answer that is that close, and we will get it in time polynomial for that constant. But this is a fairly weak definition, because there are certainly then better and worse polynomial time approximation schemes. We can have a polynomial time approximation scheme for P, which is such that we can find a 1 plus epsilon approximation which runs in time n raised to 1 through epsilon. What this means is that if we want to find a 1% approximation, that is, we have chosen epsilon to be equal to 0.01, then the algorithm will run in time n to the power 100, that is n to the power 1 through 0.01, which is of course fantastically slow, but we will get a 1% approximation. Since we consider this 100 a constant, it is polynomial time, but it is certainly not a great result still. If we want a really bad approximation, so let's say we want the 2 approximation, then this is more or less fine. Then epsilon equals 1, so we get 1 through 1, or so we get an approximation in linear time. We can often do a lot better though. For the Knapsack problem, notably, there is a polynomial time approximation scheme which finds a 1 plus epsilon approximation in times 1 through epsilon multiplied by n cubed. So to get a 1% approximation for Knapsack, we need time 1 divided by 0.01, which is 100 times n cubed. So now the 100 has ended up in a much better place in the expression. So we have something that is actually recognizably a polynomial. So finding a 1% approximation of Knapsack is not all that difficult, which is of course fantastically convenient for us. And this is in fact the polynomial time approximation we will now figure out how to do. Before we get into that though, we need to introduce the Knapsack problem properly, because we have not seen that before. So Knapsack is a problem that as input takes a maximum weight W, which is the maximum weight the Knapsack can hold. It takes some number n objects, where each object has a weight and a value. And then we wish to find a subset of the objects such that the total weight of the subset is not greater than W. That is, we want to put them in our knapsack, and we cannot go over the maximal weight. But we want to maximize the value. That is, we want as much value to be included as possible in the knapsack within the weight limit. So we can imagine an instance. Now I need to cheat a little bit. So we have our friendly knapsack here. And we say that it can hold at most 16 kilos. We have our first object, which weighs 7 kilos and is worth $2. We use rupees, but I don't think you do not have a symbol for it, I think, so it's not quite as neat. Or possibly you do and you haven't seen it. So second object weighs 10 kilos and is worth $3. Third object, oh, this is not what I write here, weighs 8 kilos and is worth $2. And the fourth object weighs 1 kilo and is worth $1. And then what we want to solve here now is that we're going to fill our knapsack with at most 16 kilos worth of objects, and we want as much value as possible. So suppose we are robbing a store or something similar with a very small knapsack. So the way to solve this is using dynamic programming. First, we let V be the total possible value. That is, if we add up the value of all the objects, that should be big V. So remember that. And then we create a table, P, which has a row for each object, or each object number, I should say. And it has a column for each possible value between 1 and the maximum value. And we fill it out with integers. So I'm going to immediately draw this table. So we have P here. So we have four rows. The total value is 2, 5, 7, 8. So we get 1 for 1, 2, 3. I might have to squeeze this together a little bit more to fit in frame. 2, 3, 4, 5, 6, 7, and $8. And now we're going to fill this table out. And the way we're going to fill this out is that the cell on row, let us say row 2, and let's say $3, will eventually contain the minimum weight we can get away with if we choose among the two first objects and the total becomes $3. That is, the rows decide how many objects are we allowed to look at. So on row 1, we will only be allowed to choose from the first object. On row 2, we'll be able to choose from the first 2 objects. On row 3, we'll be able to choose from all 3 first objects. And on row 4, we'll be able to choose from all objects. And in each cell, we write the weight, which is the minimum weight we can get away with to achieve the value noted on the column. So what we do is that first we start on row 1. And row 1 is very easy because in each cell we just have to decide either we take the first object or we do not take the first object. And the only cell then which will get filled in is the cell where the value is precisely the value of the first object. All the other cells will get infinity. That is, there is no amount of weight we can add to actually get, let us say, $8 out of choosing to either include or not include the very first object. Then, in a next step, for all the other rows, we will simply look at the row above and consider, is it better now to include this additional object. That is, when we fill in row 2, what we will decide is that, okay, we know the best way to get this particular value using just the first object. Can we do better by including the second object? This becomes a lot clearer once we start filling in. So let's do so for this. I'm going to take the sheet. So what weight can we get away with to among the first object to get $1? It's simply not possible, because the first object costs 2, so either we get 0 or we get 2. So get an infinity there. What weight can we get away with the first object to get $2? Well, in that case, we include the first object, so we get 7 kilos. We cannot get $3 for the first object. We cannot get 4. We cannot get 5. We cannot get 6. We cannot get 7. And we cannot get 8. And it's a very ugly infinity sign. Okay, so then we take, now we may include any of the first 2 objects. So we still cannot get to $1 in no way. So how can we get to $2? Well, there's 2 possibilities. Either we just keep the first object, or we include the second object, or we possibly just, or in that case, what will happen here? We cannot include the second object because it costs $3. So the only way is that we keep. So choosing among the first 2, we just copy from the row below, row above, I should say. $3. Here the possibility then is that we can choose not to include anything from the row above. So we take the 10 kilo of the second object. We can achieve $3. So we write in 10 kilos. $4. This is not possible either, because if we look here, so we have $3 from this one and 10 kilo. So what we need is an other dollar, but it's not possible because the weight is infinity, so the total is infinity. $5. Here we have, so just including this one does not work, because that does not get to 5. So we can include this one, which is 3 plus whatever is in 2 here. So if we sum those 2, so we have 10 kilo from here, and we should take the 7 kilo from there to get to 5. So we have 17 kilos. So here we get 3 from this, so we need another 3. So we look at this cell. No, not possible. We get infinity. We get 3 from this. We could look at 4. Not impossible. 3 from this, so we should need a 5. Not possible. So get an infinity. The third object, so 8 kilos for $2. You cannot get anything there. So here then, we can include just this object, which would get us $2 for 8 kilos, but 7 kilos is better. So we keep from the row below, above here. So $2. So we check then on the row below, the row above, what can we get for $1? Infinity. So we cannot get actually to $3 either. 4, so $2, and we add $2 here. So 7 plus 8, we get 15. 5, and we check here. So we have 2 from the object, and we can add this thing. That comes to 18 kilos. But we can already do $5 for 17 kilos from the above. So we keep that case. That is, it's better not to include this one, because we already could make a 17 kilo $5 pile using the first 2. So 6, and then we check over at 4. Not possible, so this will be an infinity. 7, so we need to add 5, so this would be 17 plus 8 kilos, which is better than the infinity we have above. So we'll land at 25 kilos. And then we get this, where $2 plus 6 gets us, once again, infinity. And we continue with the very last row. So 1 kilo for $1. So that's better than the previous of infinity. So we have this. Getting to 2, we would need these 2. So that's infinity. Getting to 3, we would need this one. So $1 plus 2. So we get 8 kilos. Getting to 4, we would look at 3. Infinity, so we keep from above 15 kilos. Here we need to look there. So here again we have then adding the $1 object to the $4 pile here would actually get us down to 16 kilos. which is of course an improvement. Adding a $1 object here to the 17 kilo pile gets us to 18 kilo for this case. Here we get keep the 25 kilos because we cannot add this. And finally we get 26 kilos here then by adding the 1 kilo object to this one. So this got a little bit messy, but I mean it should be fairly clear that in this way we can just go through linearly and figure out how to solve the knapsack problem. Yeah, specifically we should say how we actually extract the answer as well. So the limit is 16 kilos. So all we do is that we start from, okay, what can we get for $8? 26, so that's no good. 7, 25, no good. 6, 18, that's no good. However, for $5 we can get away with 16 kilos. So this is the answer that we are able to take objects for 5 kilos. $5. 16 kilos, we get $5 worth of objects, which should be this one, and this one together. Hopefully this was reasonably clear. So we return the maximum we extracted from the table. So this solves the knapsack problem in time on the order of, so we have n rows and we have v columns. So we get a time which is n times v on the order of, which certainly looks polynomial, but as it happens, knapsack is NP complete. It's listed as one of Karp's original 21 problems, but it actually has a very different definition from the one we use here. So it is proven elsewhere. But have we then with this polynomial thing proven that p equals np? Well, certainly not, because the thing about v is that it is actually exponential in the size of the problem. That is, if the objects have values that are very high, so let's say that the first object is worth 2,390,150,000, it's not a long value to write down. So the problem itself does not get long from having a large value, but what happens is that we create an absolutely fantastically large table. So we would have a table with 1 billion columns, or rather with 2.39 billion columns. Which of course makes this approach entirely hopeless without making the problem itself large. So this sort of brings back why then knapsack is actually NP complete. But as it happens, we can actually still rescue this situation. If we start by, let m be the maximum value among the values included in the knapsack problem. So in the example case here, we would have $3, but more usefully, we would imagine that it's a very large number. We assume, for simplicity, that all the weights of objects, each individual weight, none of them is larger than the entire knapsack, because in that case, it's of course pointless, because that object cannot go in the knapsack, so it will never be in any solution. So we can remove those from the start. This means that the optimal answer, that is the absolutely best packing of the knapsack, must be at least m. That is, we have to be able to include at least one object into the knapsack in the solution, since all objects are possible to fit into the knapsack. And so the worst case is that we take the most expensive object, put it in the knapsack, and we're done. If we now compute s to be equal to our epsilon, so the epsilon has been chosen by a user who wants an approximation of this knapsack problem, to be epsilon multiplied by m, so we take epsilon times the size, the value of the most expensive object, and we divide it by n. This is what we will call our scale factor. Then we apply the same dynamic programming solution we just saw to solve the knapsack instance that has still the same maximum weight w. No, wait, this is wrong. So it should, no, this is right. It has the same maximum weight w. It has the same number of objects n. It has the same weights on the objects, so each object weighs w1 up to wn. However, the values we now truncate by the scale factor. That is, we take each object, we divide it by the value of each object, divide it by s, and we round down. So for example, if the scale factor became 100, and we had an object that is worth, let's say, 2,150, then we will instead say that this object is now worth 21. So we just removed the last 2 digits off of the value of the object. So we will get some kind of solution back from this dynamic programming solution. And the table this dynamic programming solution will have to make is all the smaller, thanks to the fact that we have now decreased the value of all objects. If we take the result this dynamic programming solution gives and multiplies it by s, we will get something that is not quite as large as the proper solution to the knapsack instance. However, it will not be too far off because we have scaled all the values down by s, and then we have truncated away some of the numbers at the end, and then we multiply by s. We do not get back what we have truncated, but we scale by everything we kept back up again. In fact, what we will get is that in each value will at most be s off. That is, if s became 100, so we take each value, we divide by 100, we round down, and then we multiply by s at the end. At most, we have lost a value of s. So in fact, we have lost slightly less. We have at most lost value of 99 if the scale value s was 100. We multiply that by n. So absolutely worst case, all of the objects were included, and every object lost a value of almost s. So this is the most value we can have lost in this approximation of knapsack. So we take n times s, and s was epsilon m divided by n. So n times epsilon m divided by n is equal to epsilon m. That is our permissible error factor epsilon times the maximal value of, or rather the largest value of any object. So that is how much too low the solution can become. And we know that the optimal answer is at least m, which means that this becomes a factor 1 plus epsilon off of the optimal solution. That is, if we are epsilon times m too low and the correct answer is at least m, then this is at most a factor 1 minus epsilon, I should probably say, away from the correct answer, which is exactly what we wanted. We want a 1 plus epsilon approximation, and we got it. We will not be more than a factor 1 plus epsilon away from our correct answer. It is also runs in polynomial time, because now the algorithm will again construct one of these tables which will contain one row for each object, and it will contain one column for each possible value between the least value and the maximum value. So if we then sum up each object's value divided by the scaling factor s and truncated, so this is all the columns that will exist, this sum, because this is total possible sum in the dynamic programming solution for the approximated case. Then we have basically then n times, rather we have n instances of values, each of which is at least m, which means that we can say that, well, this is at least less than n times m divided by s. So we have removed the truncation, but that just makes things larger. And we have replaced the values by m, but this also only makes all values larger. So this is the absolutely most number of columns the table can have. And if we again expand the s, what we will have is that we have n times m divided by epsilon m divided by n. And if we cancel out the n's and move, or rather we move the n up to the square and we cancel out the m's, then we get n squared divided by epsilon as the number of columns in the table. And this means with n rows and n squared divided by epsilon columns, we get a table which has a total of 1 divided by epsilon times n cube cells. Well, I should say then, and this then means that we have a polynomial time approximation scheme. It approximates with a factor at most 1 plus epsilon off, and it does it in time that is on the order of 1 divided by epsilon times n cube, because filling in the table is a linear procedure. So this is precisely what we wanted. So there is a lot more stuff one could say about approximation. Very notably, it is interesting to prove that some problems are not approximable. So there are some problems that cannot be approximated to even any kind of constant. So you cannot get a C approximation for any C. But this is slightly more complex. But it's overall sort of an area that is well worth doing some reading in. It's both practically useful, and a lot of the algorithms and theory surrounding it is rather clever. So thanks for listening, and any questions?